Hey everyone, last time we were talking about what it means to be algebraic over a field K. We have this minimal polynomial. We also have K adjoint alpha. We have the connection between K adjoint alpha and the minimal polynomial and the evaluation mapping. And we're going to sort of continue this study now. So our next theorem goes like this. So let's take an extension. So let's let L over K be an extension. And we're going to take an element, let's say alpha, in capital L. Now, this is really kind of an amazing theorem here. So it goes like this. So then alpha is algebraic over K if and only if the degree of the extension K adjoint alpha over K is finite. And we're going to say a little bit more here. So moreover, if alpha is algebraic over K, then the degree of the extension, right? We know up above that it's finite, and we can actually say exactly what it is. It's equal to the degree of the minimal polynomial. Okay, now for the proof, so here we go. In the proof, in the forward direction, we're going to assume that alpha is algebraic. So let's assume alpha is algebraic over K, and the proof is going to go like this. In the forward direction, we're going to assume that it's algebraic over K, and we're going to go straight to showing, right, that the degree of the extension is equal to the degree of the minimal polynomial. Of course, that will allow us to conclude that the degree is finite. So let's give this a number. So let's say and write n for the degree of the minimal polynomial. Now, okay, I want to show that this degree then is equal to n. Remember, the degree is the dimension of K adjoint alpha as a vector space over K. So to find the dimension, right, I mean, the dimension is the number of elements in a basis, so I want to produce a basis. And so we're going to say it like this: claim, right, and we're going to get an explicit basis here. The set 1 alpha squared up through alpha to the n minus 1. So the claim is that this is a basis for K adjoint alpha over K. So now to prove this claim, so proof of the claim, first let's show that it's linearly independent. So suppose that what K0 plus K1 alpha plus K2 alpha squared plus dot 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 plus K sub n minus 1 alpha to the n minus 1 equals 0, right, for some choices of K. So for some K sub I in capital K. All right, so we've got a linear combination adding up to 0, and we want to then to conclude, right, that all of the K's have to equal 0. Well, you can think of this linear combination right here actually as a polynomial where you plugged alpha in. So that's what I want to do next. So letting f equal k0 plus k1x, so I'm just going to replace the alphas with x's, plus dot 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 plus k sub n minus 1 x to the n minus 1. This is a polynomial in k bracket x. We have, well, let's see now. We know that when you plug alpha into this polynomial, right, f of alpha is equal to 0, which means that f lies in the kernel of the evaluation map. So we have f is an element of the kernel of the evaluation map, E sub alpha. And we showed last time that the kernel of E sub alpha, right, that's an ideal, right, and the minimal polynomial is the unique monic generator of that ideal. Okay, so what does that tell us? Well, let me see now. The degree of m sub alpha is equal to n, and we have a polynomial of degree strictly less than the degree of the minimal polynomial. That can only happen if that polynomial is actually the 0 polynomial. Right, so since the degree of f is strictly less than the degree of the minimal polynomial, the only way for this to happen, so we have that f has to be the 0 polynomial, meaning that k0 equals k1 equals dot 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 equals k sub n minus 1, which equals 0. Therefore, our set 1 alpha up through alpha sub n minus 1, that set is linearly independent. Okay, so there's half of the proof of the claim. Now I need to show that this set also is a spanning set. So that means that I need to choose some element, some arbitrary element in K adjoint alpha and show that it can be expressed as a linear combination of 1 up through alpha to the n minus 1. So now, choose, or maybe let is better. Let Z be in K adjoint alpha. Now, last time, we got a characterization of what the elements of K adjoint alpha look like. They look like a polynomial with coefficients in K where alpha has been plugged in. All right, so that was our last theorem. So by theorem 1.4b, there exists I guess I can use k's again. So k0, k1 up through k sub t in K, such that Z is equal to K0 plus K1 alpha plus dot 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 plus K sub T alpha to the T. Yeah, right, so why is this? Well, because last time in theorem 1.4, what we show is that K sub alpha actually is the image of the evaluation map. Right, so I guess I should say because k sub alpha equals image of evaluation at alpha. Okay, now what am I trying to do? I want to show that z lives in the span of this collection of vectors right here, and the problem is we don't know about t. I mean, t is just some number greater than or equal to 0. It could be much, much larger than n, so or n minus 1. So what we actually want to do is show that we can kind of squeeze things down, and so that we don't need this gigantic number t, right? We only need this small collection right here. So, so now there exists, what I'm going to do is run the division algorithm now. Oh, I need a polynomial, sorry. Let's call it something. So letting g equal k0 plus k1x plus dot 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 plus k sub t x raised to the t. Now I'm going to apply the division algorithm to g. So there exist q and r in k bracket x with the degree of r. I'm running the division algorithm where I'm going to divide the minimal polynomial into g. So with the degree of r strictly less than the degree of the minimal polynomial, which we know is n, such that g is equal to m sub alpha q plus r. All right, so if you want, write yourself a note. I just applied the division algorithm. So now, what do we know? What do we know? What do we do? Oh, okay. So now I'm going to evaluate, right? So now E. I just got lost here. Right. Oh, yes, of course. Sorry. Now I'm supposed to plug alpha into this because we know that that's equal to z. So now z, that's equal to evaluation of g at alpha. So e sub alpha of g, which equals e sub alpha of m alpha q plus r, which is equals e sub alpha of m alpha e sub alpha of q plus e sub alpha of r, right? Just using the fact that we've got a homomorphism. We know that this is equal to 0, so this part's equal to 0. So that's equal to e sub alpha of r. And where does this live right here? Well, r has degree less than or equal to n minus 1, so that when you plug alpha into r, you get something that's in the span of 1 alpha all the way up to alpha to the n minus 1. So this is in the span of 1 alpha dot 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 up to alpha n minus 1. Therefore, the set 1 up through alpha to the n minus 1 spans k adjoint alpha. Okay, so that takes care of the forward direction. So now we need to just finish off with the reverse direction. So now what we're going to do, so here we are, reverse direction. If k adjoint alpha over k is finite, let's say it's equal to some number n. So if the degree is equal to some number n, so if it's finite, then if we look at this collection of vectors here, 1 up through alpha raised to the nth power, there's n plus 1 vectors here. That has to be a linearly dependent set. So this is linearly dependent. And so what does that mean? So then there exists k0, k1, up through k sub n, not all 0. Such that when we look at this this linear combination, k0 plus k1 alpha plus dot 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 plus kn alpha to the n is equal to 0. We get a non-trivial linear combination equal to 0. And then so letting I don't know, we're basically done. Yeah, I mean this is our polynomial. So but okay, let me just finish it off. So letting h equal k0 plus k1x plus dot 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 plus k sub n x to the n, we have, oh, and this is a polynomial in k bracket x, of course. We have h of alpha equals 0. And so alpha is algebraic over k. Okay, so that completes the proof. It's a nice proof. I really like this. It blends a lot of the ideas that are going on here, especially this interplay between linear algebra and the study of polynomials. And we're going to see that this proof, or this theorem, is very useful also. So let's look at a couple of examples now. As a first example, let's compute let's compute the degree of the extension q adjoint alpha over q, where alpha is a complex root of the polynomial x cubed minus 1. Right, so roots of this polynomial right here, these are the third roots of unity. And so those roots, so let's say it like this, so roots of x cubed minus 1 are, well, they look like e to the 2 pi I n, 2 to the, yeah, oh no, I guess n's fine, okay, 2 pi I n over 3, where n equals 0, 1, or 2. And so then if you actually compute this, who they are is, it's 1, and then it's minus 1/2 plus or minus I root 3 over 2. If you just do the trig, you'll see that these complex numbers correspond to those 3 complex numbers. And so what we're saying then is alpha is minus 1/2, and then it doesn't matter, plus or minus I root 3 over 2. Now, if you, however you want to think of this, if you factor this polynomial, run the division algorithm by dividing x minus 1 into x cubed minus 1, and the result, the divisor, the dividend, the quotient, is going to be x squared plus x plus 1. So, so you can say, so m sub alpha is x squared plus x plus 1. It's easy to see that this polynomial is irreducible over q. You can just use the quadratic formula. And so this polynomial is the least monic polynomial for which, let's just use the plus, so minus 1/2 plus I root 3 over 2 is a root. That tells us this is the minimal polynomial. And so, remember now, the degree of the extension equals the degree of the minimal polynomial. And so, the degree of the extension, q adjoint alpha over q, is equal to 2. And by by the proof of our previous theorem, we actually know who a basis is. So a basis for q adjoint alpha over q is 1 together with alpha, like that. Let's do another example. Let's find a basis for q adjoin root 2 and root 3 over q. Okay. So here's how it goes. So first, let's just note q adjoin root 2 and root 3. What that is, you can think of it as q adjoin root 2 and then adjoin root 3. All right, so you can form this extension field one number at a time, one element at a time. And so if we wanted to know the size of our basis, right, the degree of the extension q adjoin root 2 root 3 over q, according to the Tower law, that's going to be q adjoin root 2 root 3 over q adjoin root 2 times q adjoin root 2 over q. So if I could find each of these numbers, that would tell us how many basis elements we need for q adjoin root 2 and root 3. Also, in the proof of the Tower law, if I find a basis here and I find a basis here, we can find a basis for this one by mixing and matching the two bases here, right? So by multiplying from each of the two sets. So let's look at each of these vector spaces individually, or these extensions individually, to find who the bases are. So first of all, the minimal polynomial, let's just do it like this. So m sub square root of 2q. Remember, now we're going to have to be specific about which minimal polynomial we're talking about, right? Because we have scalars coming from two different fields in this case. So the minimal polynomial for square root of 2 with respect to q, well, okay, that's obvious, right? It's x squared minus 2. And so a basis for q adjoin root 2 over q is just 1 and square root of 2. Okay, so now so let's say note that if we look at the polynomial, so now what I want to do, I want to think about the degree of this extension right here. So by adjoining root 3 to q adjoin root 2, what happens? Well, what I want to do is find a minimal polynomial. And so first note that x squared minus 3, that's definitely a polynomial in q adjoin root 2 bracket x. So nothing surprising there. But now the question is it the minimal polynomial, or is there a polynomial of smaller degree with coefficients in this field right here for which square root of 3 is a root? And so, I mean, the answer is going to be no. And so to rule that out, what we need to do is show, well, let me write this now. So, say and x squared, we know how to factor x squared minus 3. It's x minus root 3, x plus root 3. So if there's going to be a polynomial of lesser degree, it would have to be that polynomial right there. And so if we can show that root 3 does not live in q adjoin root 2, then we'll be done. We'll say, well, then this polynomial does not live in here, so this is the polynomial of smallest degree for which root 3 is a root. Okay, so to show that the minimal polynomial for square root of 3 over q adjoin root 2 is equal to x squared minus 3, it suffices to show that root 3 is not in q adjoin root 2. And good thing we found the basis for q adjoin root 2. It's right there. So we know what all elements of q adjoin root 2 are now. So if we're going to go by contradiction here, so if square root of 3 is in q adjoin root 2, then there exist, say, a and b, a couple of rational numbers, such that square root of 3 is equal to a plus b root 2. I'm going to square both sides, so we can say then 3 is equal to, this will be an a squared plus 2b squared plus 2ab root 2. If these are going to be equal to each other, then this part with the square root of 2 has got to be gone. So either a or b has to equal 0. And so AB has to equal 0. If A equals 0, okay, then this part's gone and that part's gone, so we'd have 2b squared equal to 3. So B would have to equal and in fact, let's write it the other way around. Square root of 3, I guess plus or minus square root of 3 halves. That would have to be equal to b, but b we know is a rational number, so that's obviously a contradiction. If b equals 0, so then all of this stuff is gone. We'd have a squared equal to 3, right? So then plus or minus root 3 equals a, that's in q. So in both cases we get a contradiction, which means that no such a and b exist, which means that square root of 3 is not in q adjoin root 2, which means that this is our minimal polynomial. So a contradiction, let's say a contradiction, or this contradiction allows or leads us as a consequence. As a consequence, the minimal polynomial for root 3 over q adjoin root 2 equals x squared minus 3. And so, the degree of the extension q adjoin root 2 and root 3 over q adjoin root 2 is equal to 2 with a basis. So with basis for q adjoin root 2 root 3 over q adjoin root 2, that basis will be 1 and square root of 3. So now, we write down the final answer. So a basis, and this comes straight from the proof of theorem 1.4, I guess it was, our last theorem. Well, not the last theorem of today, but the theorem from last time. A basis for q adjoin root 2 root 3 over q. So what do? We have the basis, our other basis, I know I ran out of room here. We had our basis 1 and root 2. That was for q adjoin root 2 over q. Here's our basis. Now we multiply, take 1, multiply it by those things. Take root 2, multiply it by those things. Those 4 elements. Right? The Tower law tells us that our dimension is going to be 4, right? 2 times 2. And the basis is going to be 1, root 2, root 3, and then when we multiply root 2 times root 3, we get square root of 6. So that's it. That's just a direct application of the previous 2 theorems that we have, right? Understanding the minimal polynomial and understanding how the proof of the Tower law allows us to come up with bases for, say, more, for extensions, right? Allows us to concoct the basis for this right here. What are we going here? Oh, we're good. Okay, so I wanted to prove one more theorem. So this is theorem 1.6. I'm going to start off with an extension, so let's let's say it like this: if L over K is an extension, then this set right here, which your book uses the notation L sub A, so it's equal to the set of all alpha in L, such that f of alpha equals 0 for some f in K bracket X. This set right here is a subfield of capital L. Now, who is this set? So let's see, it's the set of all elements in L that are roots of polynomial in K bracket X. This is the set of all algebraic elements, the elements that are algebraic over K. So, and that's where that little a comes from, algebraic. So L sub A is the set of all alpha in L that are algebraic over K. Well, okay, fine. L is a field, which means it's a ring. So to show that this is a subfield, I want to show that it's a subring that is closed under inverses, right? Right. Or another way to say it: every non-zero element of L sub A has to be a unit. So for the proof, let's let, say, alpha and beta be in L sub A. Let's show that alpha minus beta and alpha times beta are in L sub A, and also that alpha inverse is in L sub A when alpha not equal to 0. Right? So closed under subtraction, multiplication, and inverses. Now, okay, so what does it mean to live in L sub A? It means that you need to be a root of a polynomial. So one way to go about proving this would be showing to show, let's say this way, to produce a polynomial for which alpha minus beta is a root, and then to produce a polynomial for which alpha times beta is a root, and then to produce a polynomial for which alpha inverse is a root, given that we know that there are polynomials for alpha and beta. There's a polynomial for which alpha is a root, there's a polynomial for which beta is a root. But you know what? This is difficult. So to prove it directly, let me write this down. It's sort of a comment, it's not really part of the proof, but to prove this directly, we would need to produce polynomials in K bracket X that or for which with polynomials for which alpha minus beta, alpha beta, and alpha inverse are roots. But I don't even know how to do that. I mean, there is some polynomial running around for alpha and another one for beta, but how to, using that, produce polynomials for these three, that would be a pain, right? So this is difficult. Instead, here's what I want to do is kind of do this indirectly. I'm not going to produce explicit polynomials for each one of these three. Instead, we want to say, oh, okay, what this is really saying, right, is we need to show that alpha minus beta is algebraic over K. Same thing from alpha times beta and alpha inverse. And we could do that using our previous theorem. All we would need to do is show that the degrees of the extensions are finite. If I can show that the degree of K adjoint alpha minus beta over K is finite, then I know that alpha minus beta is algebraic over K. And so that's what we're going to do. So instead, I guess this is still part of this comment, right? So that's difficult. So instead, we apply theorem 1.5, right? Show that K adjoint alpha minus beta over K is finite. I'll say etc. So, okay, so let's set that up. Now, note that since beta is algebraic over K, beta is also algebraic over K adjoint alpha. If you're the root of a polynomial with coefficients in K, then you're definitely the root of a polynomial with coefficients in K adjoint alpha. I mean, you're the root of the same polynomial. And so what that tells us then is that, well, let's say it like this. So by theorem 1.5, the degree of the extension K adjoin beta, K adjoin alpha and beta over K adjoin alpha is finite. Also, alpha is algebraic over K, so also K adjoint alpha over K is finite. Once again, by theorem 1.5, right? We knew that alpha is algebraic over K. So now I can apply the Tower law. So by the Tower law, the degree of K adjoint alpha beta over K. So what that's going to be according to the Tower law, it's going to be this finite number times this finite number, which gives us a finite number. So now notice this. So since alpha minus beta is an element of K adjoin beta. Oh, no, in fact, let me say it different. Let me say it better. It actually goes like this. Since K adjoin alpha minus beta is a subset, so now what we have, this is a finite dimensional vector space, which forces K adjoin alpha minus beta to be a finite dimensional subspace. So since K adjoin alpha minus beta is a subset of K adjoin alpha and beta, we have that the degree of K adjoin alpha minus beta over K is finite. And so alpha minus beta is algebraic. Or in fact, let's just say it like this. Alpha minus beta is an element of L sub A. And then similarly, alpha beta and alpha inverse, when alpha is non-zero, are elements of L sub A. Therefore, L sub A is a subfield of capital L. This is a, these proofs are really, they're maybe not completely obvious at first, right? I mean, your first inclination, okay, what's the definition of algebraic? It means you're the root of a polynomial. Let's try to find a polynomial. But our previous theorem tells us that we don't always have to produce the polynomial explicitly, right? All we need to do to conclude that something is algebraic, and a particular single element is algebraic, is to show that when you adjoin it, right, it gives you a finite dimensional vector space. So computing the degree is all you need to do. Okay, so that's a good place to stop. We'll see you next time.